momentum equation for a control volume. So, in the momentum equation, what we do is we say beta is equal to velocity. So, B will be equal to volume integral of beta rho dV. So, this is volume integral of rho V times dV is equal to so therefore B, if beta is the velocity, B will represent the linear momentum of all the particles which are present in the control volume. So now our Reynolds transport theorem says dV by dt is equal to volume integral of this is, if I now just in the Reynolds transport theorem put beta is equal to V. Now as far as this equation goes, there are no restrictions on this, because our control volume could be fixed, it could be deforming. If it is deforming, then the V dot NDA, which is there on the right hand side, will become V relative. Okay, only the second V there. The first V will stay as it is. But then, what is dV by dt of a system of particles equal to? We know from Euler's first axiom or Newton's second law for a system dV by dt is equal to sum of external forces. Now, when we use this relation, then the restriction comes that V then the restriction comes if we say force is equal to, or I should also put a actually what I should be writing here is, instead of dV by dt, this is made a slight mistake here. Please correct this. Because now B was equal to P, the linear momentum. So therefore, dP by dt is equal to this, and therefore dP by dt is equal to sum of external, and that comes with the same restriction. So given this, what we get is, if velocity is measured with respect to an inertial reference frame, then sum of F external on the control volume Okay. So now let us look at, so how this is the force equation. And how do we use it? So let's look at some observations which we get from this. The first thing which we get is that this is a vector equation and it can be split into components. So for example, what is the x component of this equation? X component will be sum of fx is equal to d by dt of the volume integral of Vx rho dV I just all the vector terms I write as a scalar. Now what happens to V dot n? Do we consider only Vx here or does V dot n stay as V dot n? See, just as I am writing now x components, what happens to V dot n? Do I write it as V dot n or do I write it as Vx nx? V dot n. What is the role of V dot n? It is telling us the mass flow rate which is going out. And the x component of velocity of that mass flow rate will give us the momentum in the x direction. So therefore, the V dot n will stay as it is. You will not split it up into Vx, Vy, Vz. Because the vector part is only with the vector V. V dot n per se is a scalar. So therefore, that will not be touched and this will remain Vx times rho V dot n dA. Okay? So that is the first thing. Now secondly, if we look at the integral Cs rho V dot n dA. Now what you will realize is that there are two terms which have a sign. One is Vx. Depending on how you have chosen your x, y, z, Vx, the way it is coming in, will have a sign. If your x is going positive, Vx is also positive, then Vx is positive. You take your x in the minus side, in the left side positive, then Vx will be negative. So one sign will be of Vx. Which will be the other sign? Of rho V dot n, V dot n. The second sign will come from V dot N. And this is positive if flow leaves and negative if flow enters. Okay? So this V dot N sign will also be there. Then you have to take the product of the two signs to get the final sign. Third thing, let's look at this term, partial by partiality of V rho dV. Now here, if the control volume is fixed and if we have steady flow, that is properties at a particular location in the control volume don't change with time. They may change if you move in space, but at a particular location, if let's say the velocity, density, they don't change with time. So then what will happen is, this term becomes equal to volume integral of and irrespective of the flow, this term will become 0. Because if the control volume is fixed, you can take the d by dt inside the volume integral, and because it is steady flow, things are not changing with time, this will become 0. And an example of this, let's take a very simple example. Let us look at flow through a diffuser. Diffuser means something where the velocity decreases. So this is what we call as a diffuser. Outlet velocity is less than inlet. And just to and the opposite of a diffuser is what we call as a nozzle, which would be something like this. This is V1, this is V2. So in this case, the velocity is increasing as, so that's the opposite of a diffuser. Now this what I have written actually goes only for incompressible flows. We don't show it, but if the flow becomes supersonic, that means it go above the speed of light, sound, then this actually reverses. And why does that happen? Because the density also changes in supersonic flows. So there the relation you have is not V1A1 is equal to V2A2. It will be rho VA is equal to constant. So and the density will change so much that the velocity effect, if the Mach number is greater than 1, the diffuser becomes a nozzle, the conventional diffuser, and the nozzle becomes a diffuser. And in fact, what we will also show is, it is not just the effects of velocity, the pressure also In case of a diffuser, the pressure will increase. Velocity decreases, so pressure increases. Which equation tells us that thing? That if the velocity decreases, pressure increases. We will get it from Bernoulli's equation, which we will derive probably in today's class itself, or maybe in the next class. So this is now here, if you are looking at a problem like this, and so let us say what is given to us is area changes with x, so this is the x direction. The velocity only changes with x, across with y it does not change. And if this is the term and we are supposed to evaluate, so to solve the full problem, we will need to evaluate these two components, the two terms on the right hand side. And this is the situation which is given to us. That flow is coming in with velocity v1, it leaves with velocity v2, and we are asked to make the one dimensional approximation. So here what we do is, if we choose the different type of control volumes we could choose, so we choose a control volume which is basically consisting only of the water, only of the fluid which is passing through the diffuser. Okay. So on side 1, it cuts perpendicular to the surface, to the flow. At the exit, it cuts perpendicular to the flow, and then it is going along the sides. So now, here, if I call this as 1, call this as 2, call this as 3, the circumferential surface. So 3 is the circumferential surface. 1 is the inlet, 2 is the outlet. Now, the point I am trying to make here is, if the flow is incompressible and this is a fixed control volume, now what can I say? Is the flow steady or unsteady? Is the velocity changing with time at a particular location? Flow is coming, flow is leaving, there is no change with time. So when I look at this situation, what I can say is that this is steady flow as V does not change with time. So, and because control volume is fixed, then d by dt of Vx rho dV will be equal to 0. And this you will find in many situations. Even if V was changing with Y, but if it is not changing with time, then again for a fixed control volume, you can always get this. So the term which looks like the most cumbersome will in most problems go to 0. Okay. This is one thing. Now let's look at the integral over the control surface Vx rho V dot n dA. Now On surface 1, on surface 1, this term becomes what? Let's try to see. It is Vx. So what is Vx on surface 1? What is Vx on surface 1? Which is surface 1? Surface 1 is here. What is Vx there? V1 plus or minus? Plus, is it Vx is positive or negative? It's positive. It's along the x direction. So Vx is equal to V1. Then rho V dot dA will be what? Rho 1 V1 A1. And is it plus or minus? Will rho V dot dA on surface 1 be positive or negative? How many say negative? How many say negative? How many say positive? A lot of people have no opinion. Only 5 people raised hands in. Now here Vx is equal to plus V1 rho V dot NdA. This will be minus rho times V1A1. So this term will become equal to minus rho V1 square A1. On surface 2, Vx is equal to V2 rho V dot NdA is equal to plus rho V2 A2. So the term becomes rho V2 square A2. Now the most difficult, so these two are straightforward, and see this is what happens in one dimensional approximation. If Vx was changing with y, then I would have put V1 as a function of y, V2 as a function, in V dot n again I would have put V1 as a function of y, and then I would have had to integrate with respect to y. But if it's constant, then we get these type of terms. And what happens on surface 3? Surface 3, Vx is changing, but what is V dot n? Surface 3 is a circumferential surface. So on surface 3, Vx changes with x. So that means probably we have to integrate. But what happens to rho V dot NdA? This will be 0. No flow is crossing surface 3. So this is, surface 3 is this one, the inclined surface. So there is no flow crossing there. So therefore V dot NdA becomes 0. So you don't have to bother. And so therefore the term integral Vx and so integral on the control surface Vx rho V dot NdA is equal to minus rho V1 square A1. But in most of these problems, both V1 and V2 will not be given. You will be given only either V1 or V2. How do you find that one in terms of the other? By using mass balance. So mass balance on the other side gives you will give you rho V1 A1 let us say we can write it as m dot. So then this term will becomes equal to m dot common Okay. So if I write mass balance gives me this, let's call this as m dot. So then this becomes m dot times minus V1 plus V2. So this often in all these problems, you have to use continuity equation. And in fact, it's more basic to first use the continuity equation. So what this also tells you is that you have to first use continuity equation. Now, the third thing which we have is some of the external forces. The left hand side we have not talked about. We just talked about the two terms on the right hand side. Now, the left hand side will be the external forces acting on the control volume. Now, external forces will consist of two types. In the body force, the second term, if I take first, will basically consist only of gravity. So that means whatever weight is coming, you'll have to count it as a force on the control volume. Now, surface forces will consist of these will be the terms related to the stress tensor. So, for example, if we look at the surface 1 in the previous example, our surface 1 was basically surface through which flow is crossing. So now here there would be pressure forces and there will be viscous forces on the surface because of the flow of the fluid. Now, the pressure forces they will act in the normal direction. So, integral P dA in the normal direction will give us the pressure force. And the viscous forces will be integral tau dA in the direction perpendicular to the normal. Now, on this surface, if the pressure is P1, the area is A1, then the net pressure force the force due to pressure will be P1A1 and it will act in the direction perpendicular to the normal. Inwards will be exerted by the fluid. So, here you will get it like this. Okay. In most problems involving integral flow analysis, either we neglect the viscous force. And this will be an assumption which will be made because a lot of, when you make things like a 1D assumption, then you are automatically neglecting the viscous forces. Otherwise, the flow cannot be 1D, it has to have a profile. Or the net viscous force has to be found out. So, if you have to find the net viscous force, then you will call it as some force V or some force F, and you do all your calculations, and finally you will get this as an answer. So, either it is neglected or we find it. So, you do not have to effectively, in most of the integral flow analysis problems, do not have to bother for the viscous force. You will either integrate it all together, club it and call it some force. It may be the drag force, it may be the lift force. You will try to find that, or you will just neglect it. Now, also what we know is if there is a static case, then pressure is equal to in statics we have this pressure is equal to P atmosphere plus rho GH. Okay. But in general, in a moving fluid, the pressure distribution cannot be taken as static, because static is when the fluid does not move, then you say P is equal to P atmosphere plus rho GH. But in a general case, pressure is not equal to the static pressure and will probably have to be prescribed. Now, there is also one more thing. If the control volume cuts a solid surface or is adjacent to a solid surface, then the solid will apply a reaction force R on the control volume by the solid, and this we will call it as so if a control volume you draw such that it is cutting a solid surface, then at the cut you will say Rxi plus Ryj is the force being applied by the solid on the control volume. And sometimes it is this force which you have to find out. It may say find the force in a particular situation which will keep the body from moving. So, that force is going to come out like this. So, essentially we have to draw a free body diagram of the control volume, show all the external forces. And typically these external forces will be forces due to pressure and the reaction forces. If we neglect the viscous forces, then these will be the two forces which have to be found out, and that is what you then will be working on. Okay. Now, suppose we have a container in which there is one inlet, one outlet. The velocity with which the flow comes in is V1, area there is A1. At the outlet, the velocity is V2, area is A2, something similar. But now I've made a general container type of a situation. And let's say this is being connected to a wall like this. Now here, if I have to find, and let's say the pressure here is P1, the pressure here is P2. In fact, probably V2 will not be given. You will find that from the continuity equation. Only one of the velocities will be given. So now here, if you have to find the force on the support here, how much force is coming on the support? So I am illustrating some things which are, so suppose you have to now choose a control volume. What you do is, you choose a control volume which has any shape like this, and then it cuts the flow at an exit, and the cut which we will make will be perpendicular to the velocity, so that V dot n will be just V. Okay? And then we come here on this side, the control volume cuts here. So I have taken some arbitrary shape which is cutting. Now, on this control volume, so this is my control volume. I have flow like this, I have flow like this, and then there is a cut here. So when I show the external forces, Rx plus Ry is the force on the control volume which is being put by the support. So this Rxi, this is force on control volume by the support. Let P1 and P2 be the absolute pressures at sections 1 and 2. Now, all around what is happening, this P1 is here, and what we have is P atmosphere is acting all around. Okay? So, what I can do is, I can write P1 is equal to P atmosphere plus P1 gauge, and P2 is equal to P atmosphere plus P2 gauge. So, why am I doing this? Now, when I do this, what happens is, I can write this as P atmosphere acting on the full control volume plus P1 gauge acting at A1 and P2 gauge acting at A2. Now, a uniform pressure acting all around on any arbitrary surface will give me a net zero force. On a closed surface, when the same pressure acts in all direction, you can show by using Gauss's divergence theorem, the net force will be 0. Because net force is integral P times N dA is equal to gradient of P dV. And if P is uniform, then gradient of P will become 0. So therefore, the net pressure force, if there is a uniform pressure acting, will be 0. So now P atmosphere acting all around on the control volume will cancel, and we will be left with P1 gauge A1 and P2 gauge A2 acting in the appropriate directions. That is P1 gauge A1 and P2 gauge A2. This is the net force due to pressure. And then of course we have Rxi and Ryj. And then you will apply your equations wherever V1 and V2 are, whatever directions. So X and Y, if weight has to be considered, then in the external force you will also act gravity in the weight in the Y direction and solve the problem. Okay? So this can be then done in this way, you can solve the problems. Now this has to appropriate directions, it has to be added vectorially. Now another thing is, finally you will get from here Rx plus Ryj. This is the force on the control volume. So what is the force being exerted on the support? If Rxi plus Ryj is the force on the control volume, what will be the force on the support? It will be minus Rxi minus R. So opposite of that will be put on the support. This will be equal to minus Rxi minus Ryj. So eventually maybe in this problem that is what we are looking for. What is the force on the support? So you calculate Rx and negative of that will act on the support. Now there is one more point which I will talk about. As we have seen above, in a moving fluid, pressure is not equal to atmospheric pressure. It should change, and also pressure is not equal to P hydrostatic. But there are two exceptions. The first exception is if we have a 1D flow. So we have flow of water, let us say flow if you have a one-dimensional flow in the open channel, that means this is X or this is a fixed ground, this is the X direction, this is Y. So velocity is equal to Vxi, and Vx is only a function of X. Not a function of Y. And on the top, because the surface is open to the atmosphere, so think of it like flow of a river. We are looking at the flow of a river. So on the top, surface pressure is equal to P atmosphere, and we are looking at the flow below. So, and if we can make a one-dimensional approximation, that means Vx is only equal to V is only has only an x component, and Vx is not a function of y. That is what we mean by one-dimensional approximation. Then, in this case, it can be shown that pressure distribution can be taken as the hydrostatic pressure distribution. That means if I look at any x here, P gauge is equal to rho gh, where h is the depth. So, in this case, even though we have moving fluid, the pressure distribution will be hydrostatic. And this we will show it once we derive the differential equations. Right now I cannot show it, but we will be deriving the differential equations later in the course, and then we can easily show this. So here you can assume in situations like this, hydrostatic situation. The second situation is so if we have flow coming in from a confined surface, and this flow is now being released, flow released to atmosphere. Now here we make I have put a condition subsonic, which means that the flow velocity should be less than the speed of sound. Now, do we have an example of this type of a flow? Hose, lawn mein when you water through a pipe, if you have a pipe and through which water is coming out, then this is an example of this type, that there is flow coming in, and this is called a jet. Such a flow which is coming in from some high pressure area and then it just is being released into atmosphere. It could be flow of a liquid, it could be a gas which is being, it could be air itself which is being pumped out from some hole, let's say from a, it could be a vent of an AC or something, it's just coming out to the atmosphere. So now here what happens is, this is the flow which is coming out. Now surrounding the flow, all around the flow, pressure is equal to P atmosphere. Surrounding this jet, at the boundary, pressure is equal to P atmosphere. So then what one can show is, in this flow, if this is the normal direction, partial P by partial N is equal to 0. Whatever is the pressure on the boundary, normal to the boundary, the pressure at the exit will not change. So therefore, in this jet what will happen is, pressure in the jet is equal to P atmosphere at all points. So in a jet being released to the atmosphere, the think of the jet on the surface, the pressure is P atmosphere. So, but not only on the surface, because partial P by partial N is equal to 0, even everywhere inside the jet, the net pressure will be P atmosphere only. Again, this we will be able to show from the differential equation. When I derive the differential equation for the flow in the pipe, then I will show that dou P by dou N is very small magnitude compared to the other quantities. So it is actually not 0, it is almost 0. No, so that's what we will be able to show, that the pressure will not change. The pressure change in the normal direction in the air, it will be very, very small. So, and this will come from the equations only. When you look at the equations, you will be able to show that. So, I will be deriving the differential equations. Maybe I will give it to as an exam problem, show that after we derive the differential equations, show that partial P by. We will do that. Okay. But so therefore, in a jet, at all points, pressure is P atmospheric once the jet is free to the atmosphere. For this, of course, we have to assume that the jet surface is not very large. Like it's basically a small surface, then we will be able to get that. So, so this was the momentum equation. Now, there are a couple of things. So, if the control volume is accelerating, then we have to use a and what we can do is we can use the concept of a pseudo force to get to this solutions, but uh, so the form of momentum equation for non-inertial control volumes is reasonably straightforward to derive, but it's a piece of very bad news for you. In this course, we will not look at this. So, whether it is bad news or good news, I don't know those problems, of course, but we will not be covered in this course. Because of course, anyway, we have limited time, we have to cover more topics. So, but it can be easily done if you look at the textbooks. It's quite straightforward, and basically you will have to talk of velocity with respect to the control volume, and then things can straight away come. Similarly, another thing we will not be covering is the angular momentum equation for a control volume. And here we take beta is equal to R cross V, and B will become H about O, which is equal to integral rho times R cross V dV. And we can use Euler's second axiom to get dHO by dt is equal to MO. So if we, I'll just write the equation, will not solve any problems. If we apply the momentum equation, then we know dHO by dt is equal to moments about point O. I think there are enough examples done in APL 100 where you have seen this uh, very. So here now, if we apply this equation, then moments about O on the control volume will consist of external torques which are acting on the control volume, plus whatever comes due to surface forces, moments from surface forces and moments due to body forces. And then what you have is the equation becomes moment about O on the control volume is equal to d by dt of integral r cross v rho dv plus integral on the control surface r cross v rho v dot at d. So this is of course, as before, when you apply this, if it's a steady state and a fixed control volume, the volume integral term will go to 0. And the control surface, if it's one dimensional, then it will just become calculating m dot times rho cross v across the different inlets and outlets. Adding them up all together, that will give you the torque. And one example of this is, of course, you must have seen these rotating sprinklers. When a pipe is connected and that works, the basically the rotation of the sprinkler comes because of the moment from the exiting flow, and that causes the sprinkler to rotate. Okay. So, but the problems are involving this, we will not be doing. So, then the next thing we will move on will be the energy equation. And today I will just talk about the first law of thermodynamics. The application to the control volume we will do in the next class. Okay. So that is the next basic equation, and here when we apply the energy equation, beta is nothing but the specific energy or energy per unit mass, and this we call as small e, and capital B will be the total energy, and this will be volume integral of E times rho dV. Now the first law of thermodynamics, now this is applied to a system. This gives us of course, when you are doing JE, there is always a big confusion whether it is minus dW by dt or plus dW by dt. I think in physics books it is minus dW by dt. In chemistry books it is plus dW by dt. Because one of them talks of work done by the system, the other talks of work done on the system. So here now, in this case, E of course I have defined, Q is the heat added to the system, and W is the work done by the system, not on the system. So therefore, this will give you dq by dt minus dw by dt is equal to dE by dt, and this is equal to partial by partial t of volume integral E rho dV plus integral on the control surface E times, and once again this comes from Reynolds transport theorem, and this part is first law of thermodynamics. Now the specific energy which we talk of, this consists of the internal energy plus the specific kinetic energy plus the potential energy plus the other quantities. The internal energy, we use a symbol U. Kinetic energy, specific kinetic energy will be V square by 2, and the specific potential energy will be G times Z. And other energy could be chemical, nuclear, maybe magnetic, and this we will be neglecting. So we will take the internal, specific internal energy, specific energy as the internal energy plus the kinetic energy plus the potential energy. And dq by dt is the rate of heat addition to the system, and this heat could be added by conduction, convection or radiation. So the heat added could be by these things, and dW by dt, this is the rate of work done by the system, and this we will also call it as W dot. Okay. Now in fluid mechanics, what we often do is, if we have flow with inlet and outlet, and there is some sort of a rotating shaft, then the work which is being provided to the fluid is either being provided or extracted by the rotation of this shaft. So the work which is being done, so we are either we provide energy to the fluid, or extract energy through the rotating shaft, and this is what we say. So the rate of work done, we W dot S, this is what we call as the shaft work. Now if we have a pump, then we are providing energy to the control volume. And if we have a turbine, then we extract energy from the control volume. So basically, when we talk of W dot S, which we call as the actually the rate of shaft work, this isolates the machine element which is providing or extracting energy. And given our definition, this is work done by the system. Which will be positive, pump or turbine? This is work done by the system. So therefore, turbine will be positive, and work done by pump is energy being provided to the system. So this will be negative. So therefore, if we have so therefore work done by pump is less than 0, and work done by turbine will be greater than 0, as work done by the system is being counted. I think I will. So we have talked of the first law of thermodynamics. In the next class, we will look at the work done by the fluid elements, surface work done, body work done, etc., and then apply this on the control volume to get the energy equation. And what you will expect is which equation should come out of this. When we talk of fluid and energy, which equation comes to mind? Bernoulli's equation. So we will be able to show that this one under very restricted, this thing will transform to Bernoulli's equation. That is what I'm going to show in the next. Okay. And then we'll continue. Thank you.